In this lesson, we're looking at solving first order ODEs with separable functions, both x and y. So in this scenario, we're looking at functions of x and y being combined, and the idea is the same. We still want to group, we still want to integrate, and then we want to solve and isolate whichever variable we have to isolate. So in this case, we're looking to group the g of y with dy, and we're looking to group the f of x with dx. So we'll bring over this g of y, and it will be 1 on gy, integral of with respect to y, and we'll look at f of x dx. So in other words, we're just grouping the change in y with the function of y and the change in x with the function of x. So the approach is the same. Now we'll look at this in action. We'll go through a couple of examples. The process isn't very different from what we've looked at over the past few lessons. So in example 1, we're looking to solve the differential equation dy dx is equal to e to the power of 2x bracket 1 plus y squared. Now what we've got here is a function of y. What we've got here is a function of x. And we want to group them with the appropriate values, the appropriate change values. We want to bring the function of y over. So we've got 1 on 1 plus y squared and dy. And we have e to the 2x dx. So straight away in one step, we've got our two integrals that we need to solve. The first integral is going to be an arctan. So we have arctan of y on 1. We can think of this one as a squared and a. On the other side, we're looking at the integral of e to the power of 2x, so it means we have 1 on 2 e to the 2x plus c. Now all we need to do is isolate for y as it is the dependent variable. So we have y is equal to tan 1/2 e to the 2x plus c. And it's as simple as that. There is our solution to the given differential. When we look at example 2, it's not a big step. The extra piece of information that they give us is that when x is equal to 0, y is equal to 1, which is enough information to be able to determine a particular solution to this given differential. Step 1 is still the same. We want to go through our process to group and find the two integrals. So we can multiply by y squared, and we've got the integral of y squared dy, and we can separate this differential, so we've got our dx going across, and we've got the integral of sine squared x dx. Now we know that cos 2a is equal to 2 sine squared a take 1. So therefore 2 sine squared a is equal to cos 2a plus 1. And sine squared a is equal to 1/2 of cos 2a plus 1. So if we perform our substitution, we end up with 1/2 of the integral of cos 2x plus 1 with respect to x. Okay, so let's perform our two integrals. We have now y cubed on 3 and 1/2 of integral of cos 2x is 1/2 sine 2x and x plus c. Now as we're looking to isolate y, then we will multiply by 3. So we've now got y cubed is equal to 3 on 2, 1/2 sine 2x plus c. We can take this fraction out of the bracket. So that means we have 3 on 4, and everything inside the bracket is multiplied by 2, which gives us sine 2x plus 2x plus c. And the last thing that we need to do is the cube root here. So we have y is equal to cube root of 3 out of 4 sine 2x plus 2x plus C. And there we have it. We've got our general solution. At this point, this is where we can use x equals 0 and y is equal to 1. Now we could have done that earlier on as well, and it may have made the values a little bit nicer, but we'll still do it at this point. So we have 1 is equal to cube root of 3 on 4, and we've got sine 0 plus c. So we end up with 1 is equal to cube root of c, and therefore c is equal to 1. So our final equation is cube root of 3 on 4 sine 2x plus 2x plus 1. Okay, and there's our particular, our specific solution to the given differential. Now the last example is an applied one. So the question reads, a tank contains 30 liters of a solution of a chemical in water. Concentration of the chemical is reduced by running pure water into the tank at a rate of 1 liter per minute and allowing the solution to run out of the tank at 2 liters per minute. So we've got our tank and we've got water coming in at 1 liter per minute, and we've got water running out at 2 liters per minute. Well, the solution running out at 2 liters per minute. Now, if we assume the chemical is evenly distributed throughout the mixture, we'll be able to say that at any point in time we have 30 liters take T. That is, we're losing a liter a minute. And the concentration at any point in time will be the amount that we have, which is X, out of how many liters is left. So that would be 30 take T. Now, it asks us to show that dx dt is equal to negative 2x on 30 take T. This x on 30 take T is important. That's that concentration. So that's got to do with the rate of change. So we're looking at the rate of change in chemical with respect to time. Now, as it's running out at 2 liters per minute, this is where the negative 2 comes from. So it's a combination of this negative 2 and our concentration. So we can say pretty much straight away that dx dt is equal to this negative 2x over 30 take T. So it's a combination of that to give us a negative 2x and our concentration to give us the rest. Now B asks us to find a general solution of this differential. So we've got dx dt is equal to negative 2x on 30 take T. So we want to group this negative 2x with a dx, and we want to group this 30 take T with a dt. So let's go ahead and do that. We can say this is negative 1 on 2x dx. And on the other side, we have a 1 on 30 take T dt. Now if we take out this coefficient, negative 1 on 2 integral of 1 on x dx, we can see that's a simple integral. And if we make the numerator negative 1 here, we can see again that it's a simple integral. So negative 1 on 30 take T dt. So here we've got negative 1/2 ln x and negative ln 30 take T plus C. And now we can look at isolating x. If we can multiply both sides by negative 2, we now have ln x is equal to 2 ln 30 take T plus C. At this point, we probably want to find a value for C. So when T is equal to 0, X is equal to its original amount. We've got the total amount of chemical in there. So we have ln XO is equal to ln 30 take 0 squared plus C. So ln XO is equal to ln 30 squared, which is 900, plus c. So c is equal to ln xo take ln 900, and c will therefore be ln xo on 900. So if we put that back in, we now almost have our general solution. We've got ln x is equal to 2 ln 30 take t plus ln xo on 900. Now if we want to combine this, this becomes ln 30 take t squared plus ln xo on 900, and we have ln x on 900, 30 take t squared is equal to ln x. X will be equal to xo on 900, 30 take t all squared. So here's our general solution. Now, if we want to find the fraction after 20 minutes, then all we need to do is let t equal 20. So x will be equal to xo on 900 and 30 take t all squared. So 30 take 20 all squared. So now we've got xo on 900 multiplied by 10 squared, which is 100. X is equal to xo on 9. And the fraction remaining will be xo on 9 over the original, which is xo. And so we're left with 1/9 of the, so left with a fraction of 1/9. Okay. So a more complex application in this scenario, that little bit of applying understanding to determine the rate of loss at the start, a solution to a more complex differential, and then applying that. Okay, so that concludes the lesson. Hopefully that all makes sense and you'll be able to apply this into solving problems of your own.